Hi everyone, in this video we'll learn about spanning trees through examining this problem. And this is our problem. So we want to connect some computers, but we want to connect them with fiber optic cable. So it's not a Wi-Fi connection, there's actual cable that attaches computers. And the cables have different costs for connecting different computers. So our solution is such that we require that any two computers can communicate with each other, and then we want to find a solution which minimizes the cost, and that's the cost of the fiber optics. So by communicate with each other, we mean that if you had three computers in such a configuration, and let's call these A, B, and C, if you had connections between A and B, and then B and C, then we would say that A and C can communicate. So we don't mean by saying that they can communicate that they have to be directly connected, but if they can talk through another computer, then that's okay. So obviously we're going to represent this network of computers by a graph. And the computers are represented by vertices, that's the dots, and then connections between computers, or potential connections, are represented by lines. Those are edges. So we have vertices, A, B, and C, and we have edges. The edge AB, the edge BC. And then we'll put numbers on the edges, and that represents the cost of placing a fiber optic connection between those two computers. So maybe this one would potentially cost 10. We don't much care what the units are, and then this one maybe it costs 475. I'm just making those numbers up. So these say that we can choose to connect A and B directly, but it's going to cost us 10. We can choose to connect B and C, but it would cost us 475. And in this example, there is no possible connection between A and C. So it's not even an option. Okay, so imagine in such a network you want to solve this problem, and minimization is key. So we can easily connect all the computers, but we want to do so in such a manner that we minimize the cost. So we have the cheapest connections where any two computers can communicate, and it's minimum cost. So let's think about this kind of optimization that we're doing, minimization. Let's say that in a different network we have 4 computers, A, B, C, and D. And let's just say theoretically we've connected A and B and C and C and D. We've already chosen those connections for whatever reason, and we're not worrying about the costs right now. In this scenario, all these 4 computers can talk with each other. Like B and D can talk through C. A and D can talk through B and C. So everyone can talk to everyone else. In this case, I would not want to include this line, this edge. I wouldn't want to include that because that's a redundant edge. That's going to cost money that we don't need to spend. So in this case, we don't need, in fact, we don't even want the edge AD. So this type of structure that we created by adding the edge AD is a cycle. And before we added that, we didn't have a cycle. So in fact, you can generalize this to say that if you're going to have a solution that minimizes cost, you want to avoid cycles because those are redundant. You could remove an edge from a cycle and still have all the same connections. So we want no cycles. In whatever the solution is that we choose, we're going to pick a bunch of edges within a computer network. We're going to pick a bunch of edges that minimize cost. We want to avoid cycles for sure. So our solution when we pick edges from a graph will have no cycles. That's a requirement. And then also we need to include all vertices. Because if we didn't, then we would have computers that were left out of the network. And remember, up here we require that any two computers can communicate. And then also we need our solution to be connected, a connected graph. and that ensures that any two can talk. There's no cut where you have two groups of vertices that can't talk to each other. So these two properties, no cycles and connected, if you put those two properties together, those get a special name in graph theory, and that's called a tree. So we're going to define what a tree is, and it's a type of graph. A tree is a graph which is connected and has no cycles. So that's our definition of a tree. A tree is an important type of graph in graph theory. And then this property, including all vertices, because we're picking a tree from a bigger graph, and we want to make sure to include all vertices, that's a property that gets a name too. Including all vertices means we call our tree that we choose a spanning tree. And spanning is the new word here. A spanning tree. Spanning means we contain all vertices. We include all vertices. So we're looking for a spanning tree, and then our requirement that we minimize cost means that we want a minimum cost spanning tree. So put all that stuff together. That's what we want to look for. We want a minimum cost spanning tree. So we'll have a big graph and we'll choose some edges, and we want those edges to be a minimum cost spanning tree. So let's take a look at an actual example of a network. Okay, here's a network represented as a graph. So A, B, C, D, E, F, G, those are computers. Those are our vertices. That's how the computers are represented. And then each edge here is a possible connection. This is a physical fiber optic wire that we could place between two computers. And each fiber optic connection has a cost. And so in this example, we would want to connect all vertices A through G with a tree, so it's a spanning tree, and then we want it to have the lowest possible cost. There are a couple of algorithms that we'll look at in 2 future videos that actually produce a minimum cost spanning tree. Those are called Kruskal's algorithm and Prim's algorithm. For now, I'm just going to show you in this video what a minimum cost spanning tree would look like. So I'm going to choose some edges, and how I choose these edges right now is not important. It's just the fact that I'm choosing edges and I want these to be a minimum cost spanning tree. So don't treat this as an algorithm for choosing them. And I think that's all the edges I want. No, sorry, I want this edge too. Okay, so notice I've chosen 6 edges, 6 squiggly edges, and I have 7 vertices total. So if you just look at the edges that I've chosen, let's just draw kind of a miniature version of this. I've chosen A, G, AD, FB, and FC. So this is our actual minimum cost spanning tree. This is the tree itself. And notice it's connected because you can pick any pair of vertices and you can get from one to the other. It's spanning because all vertices have at least one edge connecting them in with the other ones. And then its minimum cost, I can't really convince you of that right now, But after you learn Kruskal's algorithm and Prim's algorithm, then you might be convinced this is minimum cost. And if you look at the weights, those are the costs of the edges. Those weights, if you add up all these weights, that's called the weight of the tree. The weight of the tree is the sum of all the weights on the edges. So it's 8 plus 3 plus 9 plus 3 plus 10 plus 2.75. That would be the weight of the tree. And this weight is the lowest possible weight that you can get for this graph. It's not to say that this is the only way you can get that weight, but that's the cheapest that you can do. Maybe there's a different graph that obtains the same cost, but this one has the minimum cost. So again, a minimum cost spanning tree is a graph that's a subgraph of the original that has minimum cost, and it has no cycles, it's connected, and it has minimum cost.